In this video, we'll be discussing the problem search pattern. We'll be solving it optimally using the KMP algorithm, but we'll discuss the brute force as well. So let's discuss the problem statement and let's see how we can solve it. Question has been asked in a lot of product-based companies previously, so it's a very important problem. So we'll be given two strings and one string is named as text string. So basically the very first string that will be given, it will be a text string and we'll be given another string that is named as pattern string. So what we have to do is we will be given one smaller string that is a pattern string and one string text string. So we have to identify, we have to find out whether the pattern string is present in the longer text string or not. If it is present multiple times, we have to return the indexes wherever it is present. So let's see the sample test cases here. If you will observe here, let's say we have been given the test case that is AB, C, AB. This is the text that we have been given, and then the pattern is basically AB. So you can always see that if a particular text has been given, so the pattern can exist multiple times. If you see here, the pattern is AB. Inside the text, starting from the index 0, the pattern exists. Okay, so I will put 0 in my answer. And then after that, if you see, so like if I'll do the indexing here, 0, 1, 2, 3, 4. So starting from index 3 as well, AB string is present again, which is our pattern. So you can see that starting from index 0 and starting from index 3, two times the pattern string is present in the text string. So we have stored both the indexes and we have returned the final answer here. Okay. Now, if you will see the second test case as well. So in the second test case, you can observe that the pattern string is AABA and the text string is given, which is very big. So if you see from which indexes we have AABA, starting from 0th index, we have got the string AABA, correct? Then after that, like starting from the 0th index, we have got the string AABA. Then after that, starting from the index 9, we have got AABA. Then starting from index 12, we have got AABA. So these are the three places like index 0, index 9 and index 12 where we can find that that the pattern string is present and starting from there. So what is the basic and the brute force approach for solving such a problem? If you will see, let's say if I was given the test case that is basically ABC AB and the pattern is AB. So let's write this. Let's say if we were given what ABC and then AB and the pattern string for us is what? Let's say the pattern string is AB here and this is the text string that we had been given, suppose. Now how can I solve it in a brute force manner? So starting from every index, what I can try to do is I can try to check every substring of the size 2 here because the pattern is of length 2. So I can try to check every substring of length 2. How can I do this? So basically, if you will observe here, what I can do here is I can basically say that if I start, let's say if my I index starts from 0, okay, and my J index is standing here in the pattern string, does the character match? Yes. Now after that, I'll move my I index further and I'll move my J index as well. Now second character also matches, then I'll move my J further and you can observe that I have compared everything and both the characters, only two characters are there in the pattern string, both are matching. So this means that this much string has matched. So starting from index 0, I can say that the substring that started from index 0, it is basically matching the pattern. So I can say that I can put this in my answer. Now after this, later on what will happen is so yes, after this what will happen here is, now like since I've stored the index 0, because starting from index 0 my substring was matching. Now we'll put the index I at 1 and we'll try to check that starting from I is equal to 1, if we check the substring, does it match with the pattern string or not. So when you see, if I match the very first character, so the very first character here is B, very first character here is A, so they do not match, so I need to move forward now. Okay, now after this what will happen is, then my I index will move further here and my J will be starting from here. Do they match? No. So this substring is also not the same. Okay, then after this what will happen is, next time my I will go here, it will start from here, we'll check the substring of 2 length here and this pattern. Now do they match? Yes, they will match here, because when you will check A and A, they will be same and B and B will be same. So you'll put the index 3 also in your answer, that starting from index 3 there's a substring of pattern length that matches the pattern as well. Okay, now how much time this brute force approach will take? Because if you see, for like for one particular index, if you see, for one particular index I have to iterate m times. Assume that n is what? N is the length of the text string. So let's say n is basically text dot length here for us. Okay, and assume that m is what? M is the length of the pattern string. So if you see here, for one, like for every index in the text, we are trying to check if from starting from that index in the text, there is a substring of pattern length that is matching or not. So for one index in the text string, we are iterating m times, because if you see, starting from this index, we checked AB. Then if in the worst case there are a lot of matches, for one index we have to iterate m times in the pattern string, because for every index we are trying to check whether there exists, starting from that index in the text string, a substring of m size or not that is matching with the pattern. Okay, now for one index it would take m time. So since there will be n indexes in the text string, so it will take n cross m time. So the brute force approach is going to take a lot of time. Can we do it more optimally? Yes, we can apply the KMP algorithm for doing it more optimally. But before that, we'll be discussing a lot of things, and we'll see how KMP algorithm uses an intuition such that will be able to reduce the complexity from quadratic, that is n cross m, to linear complexity. Okay, so let's discuss about it. So basically, what is the basic logic here? So the core fundamental logic will be that KMP will try to use the structure of the pattern to avoid any redundant comparisons. Okay, so we will try to use the structure of the pattern in order to avoid the redundant comparisons. We will try to pre-process the pattern as well. So basically, we'll be making one LPS string. We'll talk about this in detail in this video as well. And using the LPS array, which will help us to indicate how much pattern can be reused, we'll try to do what? We'll try to avoid redundant comparisons. Now let's discuss a little bit of intuition for it. Suppose that if I was given the string, let's discuss about the intuition behind KMP. Okay, before even starting for it, let's see the intuition. Now, what is the basic intuition from my side? If you'll see here, let's say if I had a string, let's say my pattern string was there, and pattern string had what? Let's say if it had something like PQ, then it had PQ, and then you had something like let's say R as well. And in this like text string, suppose you had a text string and you had PQ. Okay, then after that you had PQ, then you had P, then you had Q, then you had like let's say something like R here. Now if you see, obviously you can understand that PQ and R, so this much part is matching. But how will KMP help here? Let's understand. Like, how will KMP help me to avoid the redundant comparison? Because like the main agenda is, in order to optimize our time complexity, we need to remove the redundant comparison. Okay, so if you will observe here, like what will happen is, if you will see, when we will keep on moving, so we'll generate one LPS array. We'll talk about its building in detail, but basically as of now you can understand it will try to check that what is the longest like part that is common. So if you will see, initially there will be nothing in common, because if you consider only string P, so like there is no prefix and suffix that is common. If you consider PQ also, so for PQ, like for PQ there is no prefix and suffix common. We'll talk about this in detail when we discuss the building of the like logic. But if you'll see, without talking about the LPS array, if you'll discuss the basic intuition, so if you'll see, when I start my I from this index and my J from this index, since they will match, I'll keep on moving them forward. And then after this, one by one, what will happen is, now my I index will move here and my J will move here. Now at this point they do not match. Normally we were doing what? Whenever there was a mismatch earlier in the brute force approach, whenever we used to find a mismatch, we used to start from the beginning again. But we don't want to do that. We will do what? We'll check in the at the previous index. So if you see, like we'll check here that if this is the index here, so it will inform us that like PQ string is there. So you can see that this part is same as this much part. So what we will try to do, what we can also identify here is that this much part is still the same. Although this whole part PQRP is not the same as the expected pattern, because we expected R at the ith index, but currently we are having P. So we will not start from the beginning again. We will do what? KMP will do what? KMP will basically help you to check in a different way. So KMP will say that since your J is standing here, so don't move your I at this index, don't move your I at this index, and don't move your J from the beginning. What you will do is, you will use the pattern here. What pattern? Basically, if you'll observe, so PQ is same. Okay, and before this, how much part was common? The common part was PQ. So basically what will happen is, now your J will be like, since this much part is the same, so your J will be moved here, and the next comparison will be done from here and here. Okay, so instead of move, like you will never move your I backwards, and you will move J backwards only till a particular point. So the intuition is that I will be running throughout the array, throughout the basically text string, and it will never move backwards. Okay, by doing this, we are trying to avoid the redundant comparisons, because earlier if you see, what happened was, I expected, like initially my J was start like at while I was doing the basic comparison, so my I was standing at this particular last guy P, and my J was standing here. Now the moment they do not match, don't start from the beginning again. Use the structure, try to observe that if there is something in common. So you will see that this much part PQ, like that is there. Okay, we do not need to move our I backwards because like this much part is common here, so we can use it. So this will be the intuition that our J will move backwards only till the point that is required, and will not move our I back, because we can say that okay, if this rth character did not match here, okay, then let's move our J backward till the point that just before this, if some part was common, let's use it. So PQ was common here, so we'll use this much part and we'll keep our J here only. So that will be done with the help of LPS array. We'll discuss this as well. I hope you have understood the intuition. By doing this, what will happen? Redundant calculations would reduce, and we'll be able to solve the problem more optimally. So let's see the logic, and let's see what is LPS array in general. So LPS stands for longest proper prefix, which is also a suffix. Okay. So what is a proper prefix here? First of all, let's see that. So let's say if you have a string that is YASH here. Okay, if you have this particular string, then proper prefix would be what? Like you can say that maybe an empty string can be called as a proper prefix. Only having Y is a proper prefix. YA is a proper prefix. YAS is also a proper prefix. You should not include the complete string. Okay, so this is what we call as proper prefix. When you have empty string, when you have only Y, when you have YA, when you have got YAS. So these are the strings that can be called as proper prefix when you don't include the complete string itself. Now what will LPS of I do? Let's discuss that. So let's say if you will have if you had a test case like let's say PQ, and then after that you had something like R here. Now what does LPS array do? So if you have like LPS of I, so it will tell you what? It will tell you the longest. This is the pattern string that we have. LPS will be built on top of the pattern string that has been given. So like LPS of I will tell you what? It will tell you the longest proper prefix, which is also a suffix. Okay. So let's say if you will see initially when you have the string, when you have the basic part that is only P. If you will see, if you have only this string P, so LPS of 0 will be what? Let's understand that. So if you will see here, LPS of 0 will be what? LPS of 0 basically a string which is only consisting of a single character, that is P. You will not have any string, you will not have any string that will be of any size, because initially for the string P the proper prefix for it would be empty, so there is no matching here. Okay, but after that when we'll move, so basically because of this, LPS of 0 by default will be 0 only, because for a string which is of length 1 and at 0th index, for this much string there will be no proper prefix, so that is why the LPS for this string would be basically 0. Then after this, if you will see what will be the LPS of till index 1, if you see this much is the string here. Now LPS of 1 would be what? Now if you see LPS of 1 in this particular case, if you have got PQ, so what are the prefixes? One of them will be empty, let's not consider that. After that you'll have P and Q, you will have what? P and PQ. Now if you observe, there is no prefix and suffix that is common here, so that is why LPS of 1 here would be 0 for this particular test case here. And after this, what will happen is next up you will be having this much string. Okay, so till the index 2. So now what will be LPS of 2 here, if you'll observe? So longest proper prefix, which is also a suffix. Okay, so for this length, let's consider the case for PQP here. When you'll consider the case for PQP, what will happen here is you'll see that only one length is common here, that is this much prefix, which is also a suffix here. So that is why LPS of 2 will be updated to 1. Then after that, let's consider for the length 4 here. So what will happen is if you have got PQ here, like for this particular string, so LPS of 3 will be what here? Like LPS till the index 3. So you can see here this much part will be common, that is PQ is a prefix as well as PQ is a suffix. So that is why LPS of 3 will be updated as 2, because if you consider the substring till the index 3, the longest prefix which is a suffix as well is PQ itself, because PQ is starting from here till this index, and then PQ is at the end also. So it is a prefix as well as a suffix here. Then after that, for the last guy, that is when you'll consider the whole string, that is LPS of 4, it will be what? It will be basically when you have R here. So you can see here that there is no prefix which is also a suffix here, so that is why the LPS of 4 would be 0 here. Okay, so I have just given a basic intuition, but we'll try to see the base steps as well as the 3 cases which we need to keep in mind while developing our LPS logic because we need to write the code for it as well. So let's see what we'll be doing here. This will help us to, like, in which way? So LPS will help us, after developing LPS, we'll be able to reduce the redundant calculations in the pattern, and will, like, by using the structure of the pattern, will not have to move completely backwards. For example, the test case that I gave you, after we have developed the prefix array, like LPS array, then what will happen is, like, whenever the characters will not meet, so you will, like, ask your jth character to point somewhere here, so that whatever part was common, you don't have to compute for it again. Okay, so let's see the discussion further here. So what we will do is, for the generation of the prefix array, LPS array, what you will do is, initially, if you will see, as I told you, like, if you have got the string that is a b double a, suppose this is the string for which you are trying to generate the like prefix array, like LPS array. Now initially, if you see LPS of 0, so in this string, as of now, only there is one. If you consider only LPS of 0, that is only a single character. For this single character a, the like the proper prefixes would be empty. So for LPS of 0, you need to update 0 only, because like, for substring which is at index 0 only the substring from 0 till 0, there is no proper prefix for it. So that is why the answer would be what? The answer would be 0 for it. Initially, we'll have a length variable which will be standing at the 0th index. So what will happen here is, initially, like, you have updated the LPS of 0 as 0. Now after that, your I and length both will be standing at 0th index of the pattern. Okay, now after this, what will happen is, you will you will basically move further. So, like, initially what happened was, LPS of 0 will always be 0. That is what we have discussed, because there is no proper prefix for a single character starting at the 0th index. Okay, and after this, if you will observe further, so what will happen here is, next up, when my I index will move further to the, like, index 1, because for index 0 we have updated the LPS of 0 as 0 only. Then after this, there will be 3 cases. Okay, so when they will be matching, okay, when the ith character, and the character at the length index, they will match, we have to do something, and there will be 2 more cases as well. So let's discuss the case when what will happen is, when the character at this length index is not the same as the character at this ith index, then what we should do. So this is the case, this is the case when you can observe that the character at this length index and the ith index, when they do not match. So basically, this means what? That this basically means that there is, since the length is basically right now 0 only, and you can observe that the ith character and the character at the length index, they do not match. So that is why we'll update the LPS at the ith index as 0 only, because if you'll observe here, for the string which is basically AB here, if you have a string that is AB, what are the prefixes for it, like proper prefixes? Like, one is empty string, another one is just character A. Now this character A, is it a prefix as well as a suffix? No. That is why for the substring till AB, the answer will be updated as nothing but 0 here. So that is what we have checked, that since the part length, character at this length index and the ith index, they do not match, and the length is 0. So that is why we will do what? We'll update the answer to 0 itself, and then we'll move our index I further. So you can observe the condition is what? That when the when the character at the length index and the ith index, they do not match, okay, and at the same time the length value is basically 0, then you'll update the LPS of I as 0 and move your I index further. So now what will happen is, now your I index will move further here. Okay, the moment your index I has moved further, now what has happened, you can consider the string ABA here. Now when you have this string ABA, what will happen in this string? So when you have this string that is ABA, observe that what are the proper prefixes for it. One is an empty string, but that will not help. Another is a string A only, another is string AB. But out of this, you can observe that the string that is A, it is acting as a prefix as well as a suffix. Okay, so that is why for the string till the index 2, what is the longest length of the longest common prefix, which is also a suffix, longest proper prefix, which is also a suffix, that length is 1. Okay, that is why you have updated 1 here. So how will this be done in the code? You can observe that till this point, the length is standing at the 0th index. Now what I observe is, if what happens is, this is another condition, that if the pattern, character at the length index and the ith index, they match. If they match, then you increase the length value. You increase the length variable. So length was at 0, when you increase it, it will become 1. Okay, and then you update LPS of I. If they match, then what you do is, you do length plus plus, and then in the LPS array, you will update what? LPS of I is equal to this particular length here. So you'll update the LPS of I with this length that you have got. So length was like 0th character, that is length was at length variable was at 0, and the ith character was like at index 2, which is A. Since they match, so you increase the length variable, and then after that you update LPS of I is equal to length here. Okay, so what will happen is 1 will be there. Why? Because for the string ABA, for the substring ABA, the longest prefix, which is also a suffix, is A only. Okay, then we'll move further. So we'll move our I index further. Now what will happen is, if you see again the length character at the length index and the ith index, they match. The moment they match, we have discussed what you have to increase your length. So your length variable is right now at the index 1. When you will increase it, what will happen? When you'll increase it, it will become 2 basically. Okay, and then at the LPS of I, like at the index I in the LPS array, you will update what? You'll update this length value here, and then you will do I plus plus. You'll move your index further here. So what will happen? You have updated like the length here, like you have updated the index with the length, that is updated length was 2. So you have updated the ith index with the updated length, and then you move your I index further here. So what will happen is now like, so basically what you do is you move your I index further as well. So after that, the length is standing at this character A, and I is at A as well. Both the characters are same, so that is why you'll increase the length. So firstly you'll increase the length again, and then after that at the LPS of I, you will update this particular length, and then you will move your index forward as well. Now after this, my length will move forward and index will also be ahead, because length has increased and the index will also increase. So after this, what will happen is, if you will observe, so next up, my ith character and the character at the length index, they do not match. Now since they do not match, then what should I do? Because if you see, my length right now is how much? My length variable is having the value 3. For this 3 length, I'm not getting a prefix which is also a suffix. Correct. So if I am not getting a prefix, because I have to find the LPS for this ith index, that is, I have to find the LPS till this ith index. Now if I'm not getting a prefix which is also a suffix in this case, so should I update my length to 0? Should I start over? No, I'll try to find the next smaller prefix which can also be a suffix. Okay, for this purpose, what we should do is we should update the length variable to the LPS of length minus 1. Why we would do this? Because by doing this, what will happen is our length variable will now, okay, it will check for the next smaller prefix which can be a suffix, because we do not want to start again from the beginning. So that is why what will happen, till this length 3, I'm not getting a prefix which is a suffix as well. So we will not start from the beginning. We'll update the length variable to the LPS of length minus 1. Because of this, what will happen, right now the length variable is 3. So LPS of length minus 1 would be LPS of 2. And at LPS of 2, what do we have? We have 1. So what does this mean? This basically indicates that the length variable will now be standing at the index 1. So let's see. Now what will happen is, because of that, the length variable will point at the index 1. And now what is the advantage that we got because of this? If you will see here, so far in this particular string, we want to find the suffix ending at the ith index. Correct. Now since you want to do this, since you want to find the suffix longest suffix ending at the ith index, that is also a prefix. So length variable is standing here because you have used the fact that this particular character is basically same as this particular character. This we got how? Because of the LPS of length minus 1. Okay, now if I check the character at the length index and the ith index, they are still not the same. Since they are not the same, then again I'll update the LPS length to LPS of length minus 1. So LPS of 1 minus 1 would be 0. So LPS of 0 is 0. So that is why my length variable will go to 0th index. Okay, so every time whenever the character at the length index and the ith index, they do not match, then we want to do what? We want to update the length variable not to 0, because if you update the length variable to 0, then you will do redundant unnecessary comparisons. Instead of that, you want to update the length variable to LPS of length minus 1. This would help you to check the next smaller prefix which can also act as a suffix here. So what will happen here is, now because of this, the length variable will now go to 0, and length variable is standing here. Okay, and it matches the ith index. So since it matches, so you'll increase the length, and at LPS of I, you will update this particular length and you'll increase the index as well. Okay, and after this, your LPS array is basically prepared here. I hope you got this particular intuition here. Now let's see the conditions. So basically there are 3 conditions. Remember that. One condition I told you was when the, like, observe these conditions here. One condition is, this is the very first condition, when the ith index and the when at the ith index the character at the ith index matches with the character at the length index. When they match, we were doing what? We were updating the length, and then lps of I was getting updated to this updated length, and then we were doing I plus plus. This was the first case. But there were other cases also. Other cases like what? When they do not match. When they were not matching, then we were doing what? Normally when it was not matching, then we were planning to do what? Then we were planning to say that length will be updated to lps of length minus 1. This is what we were trying to do. So we will do this. But is this always feasible? No, this particular process is not always feasible. Why? Because if you are doing length is equal to lps of length minus 1, you're checking for the previous length, then issue can be when the length is 0. So you need to write two conditions here. What are those two conditions that you need to write? That if suppose that ith character and the length character and the length index character, they do not match, then in that case, normally if the length is not equal to 0, because if the length is 0, then you cannot access length minus 1 index, correct? Because 0 minus 1 would be minus 1. You cannot access negative index in an array. So that is why, if the length is not 0, then you'll update the length to lps of length minus 1. But otherwise, if the length is 0, then in that case you will say that the lps of I will be updated to 0 only. Okay, and then you will move your I index forward. So this is a small observation that you need to keep in mind. If they match, increase the length value, and then lps of I will be updated, will be equal to this updated length, and then move your I pointer forward. But if what happens is, if if it does not match, if the character at the length index and the ith index, they do not match, then the length would be updated to lps of length minus 1. So we'll update the length to the previous lps value to avoid the redundant comparison. Suppose if the length variable was not if the length variable is 0, in such a case we need to update the lps of I to 0, and we need to do I plus plus. Okay, so I hope you have understood these three conditions that you need to keep in mind. Let's discuss this code here. So basically, initially the length variable will be 0, and we have taken the length of the pattern string here. LPS of 0 will be updated to 0 as well, and we are starting from the index 1, because LPS of 0 has been updated to 0. So we need to start updating from index 1 here. Now what will happen is, we'll iterate until the length of the pattern, because we are generating the LPS array for the pattern string. Okay, because we are trying to see what are the patterns and how we can use them later on to avoid redundant comparisons. Okay, so if the ith character matches, if the ith index character matches the length index character, you increase the length, and then you update the lps of I with the length. Okay, and then do I plus plus. Simple step that we have already discussed. Okay, this is the first case. When they match, very good, increase the length, and then after that update the lps of I to the length variable, and then do I plus plus. If they do not match, then normal tendency would be to that we need to avoid redundant comparisons. So update the length variable to lps of length minus 1. Okay, if the length value is not equal to 0. But if it is equal to 0, then you cannot go backwards in the lps array. You cannot access length minus 1 if the length variable is 0. So that's why you will do what? You will update the lps of I to 0, because till that index you will not find anything matching, and then you will do I plus plus. So move your index further, because you cannot match anything. So these are the three conditions that you need to keep in mind when they are characters are same. Increase your index, increase your length, and update lps of I with this length, and do I plus plus. If they are not same, then you need to update the length to the previous lps value, so that you can avoid the redundant comparisons. And if the length value is 0, then you cannot access lps of length minus 1. In such a case, you'll update your lps of I to 0, and you'll move the index further, I plus plus. Okay, now after this, after this lps has been made, then we'll see the implementation of the KMP algorithm. So what you will do here is, now basically initially you will initialize the two pointers to the starting of both the strings, and one will be at the text string, another will be at the pattern string. Okay, so there will be two parts that I'll be explaining. Firstly, I'll explain it again on the sample test case that I had used for discussing the intuition of the KMP algorithm. Okay, and then after that, we'll do a step by step dry run on a bigger test case. Okay, so when the pattern when the characters matches, right, we increase both the pointers. Normal thing, when they match, you increase, and you continue your comparison. If they do not match, if the character do not match, then you will have to do what? Then you have to reset the pattern pointer. So they are saying that if the characters do not match, then you have to reset the pattern pointer. Now what does that mean? Let's discuss that over this particular test case that I was planning to discuss. Okay, so let's have a look at this intuition. If you will see here, what will happen is, let's say if my pattern string was what, let's write the text string first. Okay, I'm taking a very small example here. Let's say if my text string was the one that I took for the intuition. So you can see here, if I have pq, and then I have P, and then I have Q, and then I have got something like R here, suppose. And my pattern string is like what? My pattern string is basically having, let's say, PQ, then PQ. So let me write this, PQ, and then R here. Okay, this is what I have. Now, again, by taking this example, you'll again understand the intuition much better, because we have already discussed the logic for LPS array generation. Okay, now if you see here, initially my I index will stand here, J will stand here. Now both are same, so both will move forward. That is what the algorithm says. Okay, fine. Still they are same, characters are same, so move them forward. Still same, move forward. Move your I and J both forward. Still same, move your I and J both forward. Now I'll erase the rest of this. So yeah, now after this, I is standing here, J is standing here. Okay, by now we have discussed the LPS array generation. So let me write the LPS array for this pattern string also. So like you can see that like for like starting LPS will be 0 only. For this next part PQ, like since this is not same, so it will be what? 0 here, because if you see, if you have only P string, then there will be no like substring that will be existing of any length. So that is why nothing will be updated. Then for PQ, there is no prefix, that is also a suffix. So the answer would be 0. Then for PQP of length 1 only, I'm getting a prefix, that is also a suffix. So this answer would be 1. Then what? PQ. Okay. Then for this, like of length 2, I'm getting a prefix, which is also a suffix. So the answer would be 2 at this place in the LPS array. Okay. And then for the next one, like that is PQR, there is no prefix, which is also a suffix. So when you will run the algorithm for the LPS array, the answer would be updated as what? As 0 for this particular case here. Okay, because for this particular part, you can see that there is no prefix, which is also a suffix. Okay, now what will happen here is, after your LPS array is generated here, so like first step would be the generation of the LPS array. That would take order of m time, because you'll be iterating in the pattern string. Now if you see, like as you like after generation of LPS array, you would have moved your I and J pointers if they kept on matching. And now at this point, I observe that my I pointer is standing here and J pointer is standing here. Now the jth guy does not match. Now I do not want to move my, like we do not want to move our I pointer backwards. We do not want to move back in the text string. We don't want to do that. Why? Because if we do that, we'll be doing redundant substring comparisons, which is something which is not acceptable, because that will take a lot of time. That will be similar to brute force approach. So what we can say here is that we'll keep our I index here only, but we'll say that like if our J is standing here, we'll check at the we'll check. Okay, we'll check what? We'll check in the LPS array. So when you will check in the LPS array, so you can observe that like in the pattern string, how much part is common. So you can see that just before this part is not common. Okay, but before this much part was common. Okay, so what I can say here is that now overall everything is not the same, because like this much part and this much part, the whole string of 5 length is not the same. But like I'll not restart in the pattern string also. What I'll do is I'll say that okay, since this ith character is not matching, so I will look for this. But before this much PQ has matched. Agree? So in the pattern string, since the LPS array is already there, so what will happen is, because of that LPS array, my J pointer my J pointer would do what? My J pointer would say that okay, this much part is already common. So now my J pointer would be asked to start from here. Okay, because of the LPS array, J pointer will be standing here, because if you see for the previous, like the whole pattern did not match. The whole pattern did not match. We agree. But if you see this much part, so for this there was a length 2 prefix that was also a suffix. Okay, so that is why my J pointer can say that since this much PQ part has matched, I'll not recompare for it, and I'll start my J, like my J pointer would be somewhere here. So we'll check this guy with this guy, and by doing this, I have allowed my I pointer to stand where it is, and my J pointer also hasn't moved completely back. Okay, I hope you understand this. So we will never ask our I pointer to move backwards. Now basically what will happen, if you see when we compare, they will be same. So I pointer will move forward, J pointer will move forward. Okay, then I pointer will move forward again, J pointer will move forward, and still same. So I pointer will move forward, J pointer will move forward. Since the J pointer reaches the end, so this means we were able to compare completely. So for the second part, you can observe that for the next part now, like when there was a mismatch which happened at this particular like character P that I'm highlighting right now. Okay, so what we did was we basically used the LPS array, so that we could identify that in the pattern string which much part is common. Okay, that we can say that it is still the same. So we need to compare from the next. So we can say that now for this ith character that was not matching, we'll start checking it from here. Okay, so that's how we do what? That's how we are like avoiding going back in the text string. So we avoid any redundant movements in the text string, and in the pattern string also, like we are moving backwards very less. Okay, so this is the whole intuition. Okay, let's discuss the key points here, then we'll try to see the whole algorithm. Okay, but I hope you have understood the base case here. These are the things that we have written here. So basically, we will initially initialize the pointer to the beginning of both the strings, and when the characters match, we'll move them forward. That's fine. Okay, but if they do not match, we reset the pattern pointer to the last value of the LPS array. That is what I've said, that if this rth guy, if my j was standing here, if it did not match with the ith guy, okay, then we will update we'll update the variable to what, we'll update it with LPS of j minus 1. So basically, till the previous string, which much part was common. So in PQ you can observe that PQ part is the longest common prefix, which is also a suffix. For this much part, that is PQ in this string, we do not need to compare. So we can start from this index. That is what it says. So if they do not match, then LPS of j minus 1 would be would be the update that you will take for the previous string. From these two observations, we can conclude that there is no need to recheck. So that is what I have told you, that there is no need to recheck for you, because you do not need to check the whole pattern again, or you do not need to move your I index backwards. Okay, now let's discuss the step by step approach for this also. Okay, so what you will be doing is, initially, if you will see this bigger test case, so what will happen is, initially your I is standing where? I is standing at the index 0, j is standing at index 0. LPS array we have already prepared. I hope you get the intuition for it, because if you have got C here, so LPS of 0 will be 0. And you can see in AB also, when the string is only AB, so nothing matches. But for ABA, you will have one length. For AB, you will have length 2. And for the last guy, they will, for the complete ABC string, there will be no prefix, which is also a suffix. So the answer would be 0. So that's how they have updated the we have updated the LPS array. Now what will happen here is, if you will see the intuition here, so basically I and j initially are at 0, say they are same, so move your I and j forward, because both are same. We also have a resultant array which will show the final answer. So since ith and jth still are same at index 1, they are still same, so move them forward. I and j still are same at index 2, also they are same, so you move the indexes forward. Still at index 3, I is equal to 3 and j is equal to 3, both the characters are same. Okay, so you move them forward. Now what happens is, if you observe at index I is equal to 4 and j is equal to 4, they are not the same. So if they are not the same, so you can observe here that if they are not the same, so you will never ask your I to move backwards. You will never ask your I to move backwards. What you will do is, you will say that, okay, my jth guy, it will check in this much part, that in the pattern string, is there any part that is common that I can use? Is there any longest prefix which is also a suffix? Yes, this particular string AB. So you can see here that will say that, okay, this much part, will not will check that how much part we can use. So in this AB string, you can observe that AB is a substring which is occurring as a prefix as well as a suffix. So basically, when you will check for the LPS of j minus 1, it is returning the value 2. Why? Because it says that in the previous string substring, that is AB, there is a length of 2 size that is having a prefix which is also a suffix, AB, correct? So this is what you can observe. So that is why redundant calculations would be avoided, and this much part will be seen that yes, we have already computed it, and now my jth guy would be kind of somewhere here to check further. Let's see the steps here. So when you'll check the LPS of j minus 1 here, it will give you the value as 2, which it should give, because for this much length, the answer would be 2 for it. So what will happen is, now my j will be standing here. Now since my j stands here and I stands here, they are same, so I'll move both of them forward. And now my j is standing at index 3, I is at 5, both the characters are same, so I'll move forward. And then what will happen? Now you can see ith and jth both are same. Since they are same, we'll basically move our j forward. The moment we move, the moment we see that j has reached the end of the basically pattern string, then we need to update that at which particular index, starting from which particular index in the text string we found out the substring. So you can see that this is the substring that has matched with the pattern. It is starting from which index? Comment in the chat. It is starting from the index 2, guys, right? So how can I get it? Right now my index is at 6, okay, and j is at 4. So 6 minus 4 would be what? It will be basically 2. So this is the index from where we are getting the substring. Okay, so if I had to store, I'll store j minus I in my resultant list of integers. Okay, because starting from index 2, that is starting from I minus j index, my substring is occurring. Okay, so if my j reaches the end of the pattern string, then we will do what? We'll store I minus j in our like answer here, because the starting index would be nothing but like this much only. Correct. Now, after that, like once that is done, so for this much substring, we have found out a matching. Now we'll move our I index forward. So now what will happen? My I index will be here, and we'll restart our j, because we'll like from the next ith index, we need to start checking for the pattern again, because earlier the pattern matched. So now we'll check whether there exists another pattern or not. Okay, so we'll start our j from 0 itself. Now what happens here is my j is standing at 0. Now they match. Okay, so this guy and this guy matches. Now again so we'll move both the indexes forward. Now b and b also match. Next time what happens? A and a again match. Then what happens next? B and b match. Okay, and then what happens next? C and C match. Now after that, you can see that j reaches the end. The moment j reaches the end, then which starting from which index you found the substring? So starting from index 7. So what is 11 minus 4? 11 minus 4 is basically 7 now. So if you do I minus j, like you will be able to store the index from where the string started. Correct. So you do this, and that's how your process will be done. If you'll observe how much we have iterated ultimately, so you can observe here that if you'll see the approach. So firstly, we generated the LPS array that must have taken order of m time for us to iterate throughout the pattern string and generate the LPS array. Correct. Then after that, we iterated through the text string exactly once, and whenever we had to readjust in the pattern string, we did LPS of j minus 1, so the movements were very much restricted. So that is why what will happen is you can see that for pattern searching also, you did order of n like iteration only in the text string, and the iterations done in the pattern string are very minimal. So the overall complexity would be what? It will be order of m plus n, that is the length of the pattern string plus the length of the text string, because firstly you need to generate the LPS array, and then after that you need to iterate throughout the length of the text string. So let's discuss the code for this. Also, if you will see the time space complexity, so where in our code will be taking extra space? We'll be taking extra space because of the LPS array. LPS array will be the same size as the pattern. So that is why the space complexity for us would be order of MA, because we'll be taking extra space for the LPS array. Now when you will see the code, you'll understand things much better. So you can see here what will happen is initially my n will be equal to the length of the text and m will be equal to the length of the pattern. Once that is done, I'll declare an LPS array which will be initially marked with 0. Every element will be 0, and it will have the size same as the pattern string. Initially my resultant list, which will be storing the starting indexes from where I'm getting patterns of starting indexes of the substrings that are same as the pattern string. So that will be stored in the resultant. Okay. Then we'll call a construct LPS string here, because firstly before proceeding further we need an LPS array. So you can see here, if I'll go back to the LPS code here, which we had already discussed. So we'll run this code and the LPS array will get generated for the pattern. This is something that we have already discussed. Now, after the generation of the LPS array, we have to start a comparison. So I and j both will stand at 0 initially, starting off both the text string and the pattern string, as we had discussed. We'll keep on iterating until we reach the end of the text string. If the ith and the jth character of the pattern and the text string if the ith character of the text string and the jth character of the pattern string, if they match, we'll increase both the indexes by 1 each. That is what we have discussed already. But if suppose that what happens is if they match, well and good, we'll increase both I and j. And after increasing I and j, suppose that if my j reaches the end of the pattern string, this means what? If my j will reach the end of the pattern string, in such a case what we would try to do is we'll try to say that okay, if the j has reached the end of the pattern string, then we'll store I minus j in the result, and instead of doing j equal to 0, we'll do what? We'll do j is equal to LPS of j minus 1. Now why would we do that? Because of the simple fact that suppose if I had something this thing. Suppose if I had AB, and then suppose I had AB and I had AB as the pattern string. So suppose that I had this as the pattern string and I had this as the text string. Now what would have happened here? If you'll see, when my I would be standing here and my J would be standing here. So what will happen here is I have found a substring starting from the 0th index. This much substring is matching as the same pattern. So starting from 0th index, I have found out a substring. But should I start my J from 0? No. What I should do is I should say that if I'll check So like I can do what I can move my j to what, like once it reaches the end point here, once my j reaches the end point, like somewhere here, let's say, then what you will do is you will basically ask it to move back. Why? Because if you see this much, like pattern is same, so you do not need to move it like from the starting. You can say that it will check the previous length lps, and whatever part is common, it will start from there. So basically you can observe here that like my j will be at the end point. Now it will check j minus 1, so it will check for this whole string. What is the lps? Lps is of length 2, so basically this much part is common, so it will start from here. Okay, so j will start from here. Now what will be the advantage of this case? If you'll see, when j starts from here, now so what will happen is, since this match I moves forward, so I is now standing here. Okay, so we are not moving backwards again and checking the whole thing, because I is here. I told you that I will never move back. So because of this, when I did j is equal to lps of j minus 1, so it checked for the whole string, because j was at the end. It checked for the whole string. When it checked, so length 2 is what you got. So this much, for this much part, you don't need to check. So j will start from here. Now this ith and this jth will match. Both will move forward. Okay, and then they match. I moves forward, j moves forward. Now j reaches the end point. Again, you can say that the pattern has matched. So starting from which index? Starting from this particular index, that is index 2, you found another match. So that's how you are saving redundant calculations here. I hope you have understood this as well. Now, like these are the things that you need to take care of, because you want to avoid redundant calculations as much as possible. And otherwise, if the ith character and jth character do not match, if they do not match, then the philosophy will be very, very easy. Because if they do not match, then you will say that, okay, if they do not match and the j value is not equal to 0, if you can access j minus 1 1th index, then you'll update j to lps of j minus 1, because you'll use the lps array, and you'll use the lps array for the previous index, to avoid the redundant calculations here whenever there is no match, that we have discussed in our test case for pqr also, and for the given test case also. And like if the j value is 0, then you need to simply move your I index forward, because you cannot do anything, and at the end of the day you will return your resultant array. So I hope you have understood this clearly. And if you see this, like time complexity is what, it is order of n plus m, because firstly you are generating the lps array, that would take order of m time. Then this whole algorithm is taking order of n time. The kmp matching process is taking order of m time. So overall it will take order of n plus m time. Space complexity will be how much? So time complexity, as I said, it is going to be basically order of n plus like order of n plus m here. And the space complexity is going to be how much? It is going to be basically order of m here, because we are generating one lps array, which will be basically same as the length of the pattern string here. So I hope you have understood this. Let's see the code also, if we are able to submit it. So let's submit the code. It should work fine. Let's see. Same code that we have discussed, we have written here. So you can see that the code was able to pass all the test cases. Now this problem has been asked in companies like Microsoft and Amazon. So I hope you got a complete intuition about the KMP algorithm, and how it resolves the issue of redundant comparison or redundant movement of the I pointer and the j pointer. In case if you did, make sure to comment understood. Thank you for watching this video.